In this process, we are going to explain the discussions on the discipline of econometrics. Basically, what is econometrics? Econometrics is basically an application of the mathematical statistics to economic data in order to lend empirical support to the economic mathematical models and obtain numerical results. So it is basically an amalgamation of economics, statistics, and also applications in the real life. Now we go on to the discussions of econometrics in a broader frame. Now we actually get into the word econometrics, which means measurement. What is that? It is economic theory, followed by the application of mathematical economics, which requires economic modeling, and finally the applications. This boils down to the amalgamation between two, which is shown by the arrows. Now we go for the econometrics as a discipline. So what at a discipline we mean by? As a discipline we mean by it is a concept of an economic model. So this goes back to the difference between economic model and econometric model. In economic model, we take up two variables, dependent and independent, which are solely affecting each other. But when we go to econometric model, it is the relevance of an extra term called the error term or the random term. And thereby, we shift from an economic model to an econometric model. For example, when we see consumption is a function of income, where it is said C for consumption and capital Y for income, it is basically an economic model. But when we move on to econometric model, it implies the inclusion of the error term, which captures all the factors which affect the level of consumption other than the level of income. And that is the basic difference between the two. So we need to explore on the foundations of an econometric model. When we want to explore on the foundations of an econometric model, we need to stress on the steps that are necessary in the formulation. Step 1 refers to specification, which means relevance of error term. Now, why is error term relevant? That is very important. Suppose we are working on a consumption-income relationship, and there can be many factors which are affecting consumption other than income, as they are called omitted variables. Or it might be that consumption and income are not measured in the proper terms, so there can be a measurement error which can be captured by the error term. It also can include some of the randomness or the shocks that are existing in the model. And as a whole, it will basically dump in all the extra factors which are included not as independent variables. This boils down to the step of estimation. This is very important because when a model is constructed, the data is collected from the sample and thereby the data is estimated. And on the basis of the data, we draw some inference, and that is what we mean statistical inference. So based on the estimation procedure, we go for drawing the statistical inferences. This goes back to the third step, which is validation. Whether the result is okay or not, whether the result is consistent or not, we need to validate the model. And this validation requires to conduct some test which makes the result to be acceptable or not. And finally, we go for the forecasting. So when we go for the forecasting, we need to go for the future values or predict the future values in this case. So this basically calls on the concept of developing a classical simple linear regression model. So the foundation of developing a classical linear regression model is based on the steps which is discussed in this econometric specification and also the discipline that comes over. And thereby we go for certain ordinary least square assumptions. Because in a classical regression model, the basic assumptions need to be stated. So when we go by the assumptions and as we go one after the other, we shall be actually involving some of the basic steps which are repeated and also which must be reflected in the estimation procedure. First of all, the model is linear in parameters but not in the variables. That means we can say that the two parameters, as we always discuss in this model, is alpha and beta, and they are basically representation of the population. But we may not have the exact true representative from the sample. So in the sample, we might get a proxy variable, and so the variables might be nonlinear, but the parameters may be linear. So that is one of the severe constraints of this classical linear regression model. For example, if we estimate a cost function, then that is quadratic in nature. That means the variables are nonlinear, but the parameters are linear. Now we go to the second important assumption, when number of observations in the linear model is not lesser than the number of explanatory variables. That means the number of observations must be greater than the number of variables to be estimated. Otherwise, there will be a problem in the degrees of freedom, and this will affect the estimation process. So this has to be remembered by the researcher at all times when collecting the data or when moving for the estimation procedure. Any two explanatory variables should not have an exact linear relationship between them. This means that when we are working with a particular model, there may be many factors which are correlated with each other. For example, if we do a wage education model, like education is dependent upon the wage, then we can find out that there may be many factors which are affecting the wage. So this will make the problem of multicollinearity to come up, and that will actually affect the estimation process. Next assumption comes in where explanatory variables are independent of the error term. This is very relevant in econometrics because the error term and explanatory variable should not have any relationship. Otherwise, the problem of endogeneity will arise. So when I talk about the problem of endogeneity, it means that some of the factors in the error term are already correlated with the explanatory variable. For example, we are understanding on the determinants of FDI. So GDP is one of the crucial determinant of FDI, but there are many factors in the error term which are related with GDP, like human capital, infrastructure, governance, finance, and many others. So they can be captured in the error term, and they might be correlated with the explanatory variable. So this will pose a problem of endogeneity and will affect the estimation process. So in this manner, covariance between E and X should be 0 as per the Wallace assumption, and it should not be non-zero. Error terms should not be correlated with each other. This happens for a data which changes with time. So if we take a data on GDP and it changes over time, we will observe the GDP of the current period depends upon the last period. For example, GDP is available in annual data, so the GDP of the year 2022 may be dependent upon the GDP of the year 2021. So in that way, errors are related with each other. So it is called autocorrelation problem in the sense it is regressed on its own past value. The same kind of phenomena is observed in case of exchange rate. It is observed in case of stock price, gold price. So all these variables follow time series data, and so errors are correlated with each other. And now we come on to the last assumption, which means errors should have zero mean and constant variance. So this is very important to notify that the constant mean and the variance comes up. Henceforth, we go for the elaboration of the ordinary least square assumptions. So as we go for the elaboration, we find linear regression model in parameters. This is meant by the population parameters of the model, where alphas and betas are the two important parameters in this case. So in a two-variate regression model, we have alpha, the constant intercept term, and the slope coefficient is given by the beta, and they should be linear in nature, but the variables can be nonlinear. They can take up the square form or they can take up any other functional form. Go to the next important assumption, X values are fixed in repeated sampling. This means that when you're collecting a sample from the population, there should not be any kind of variation in the X values. So they should be same across all the sampling distribution that is collected. The third assumption says zero mean value, which means that over the samples, the error term should have a zero variance as well as the zero mean. What does it mean? It means on average, the sum total of all the assumptions must be zero. Next, we have the assumption of homoscedasticity. That means in case of a cross-sectional data, it is seen that the variance differs across the sample observations. So when we take up a data from different income groups, and if we take a heterogeneous sample, then the low income category, high income category all are mixed up, then the variance of their consumption expenditure will keep on changing with the change in the number of observations. So this will pose a problem of heteroscedasticity. So if this is present, then we cannot apply the ordinary least square method. So for application application of the OLS method, the variance should be constant. Next, we move on to the no autocorrelation. That means in case of the time series data, the error terms are correlated with each other. So there should not be any kind of dependence on one error to the other, as it is mentioned by no autocorrelation, or actually no self-correlation among themselves. If it is found, then the residuals of the estimation series will have the problem of autocorrelation, and that estimation method will not be continued. Now we move on to the zero covariance between Uy and Xi. This is basically the problem which occurs in terms of a growth equation or in terms of a panel data, where we find out that there is a relationship between the error and the explanatory variable. So the covariance must be always 0 for OLS to apply. Otherwise, there will be a problem of endogeneity in this entire data set. Next, we move on to the number of observations must be greater than the number of parameters to be estimated. This calls for taking care of n, which should be greater than k. For example, small n refers to the number of observations and small k refers to the number of parameters to be estimated. So there should be n greater than k. After that, we have the regression model is correctly specified. This calls for non-omitted variables should not be too much in the model. So when we consider non-omitted variables in the sense that they should not exert more influence on the dependent variable, if this is going to take place, then generally the estimation model will not be correctly estimated and inference will not be drawn accurately. Finally, we come to there is no perfect multicollinearity between the independent variables, because that will pose a definite problem in this entire estimation process. As we move on to the method of the least square regression procedure, we observe that particularly we have y across x. So y is basically the dependent variable, which is referred as capital Y, and capital X is referred as the independent variables, and we have different observations like x1, x2, x3 and x4. So x1 observation is given as P1, which is a combination of y1, x1. Similarly, P2 is another combination of y2, x2. And in this way, 4 such combinations are considered. We have observed in this particular diagram that there is a fitted line which starts from the intercept B1. So this is a positive intercept on the axis which starts from the B1, and it's a fitted line. Now we observe that some of the actual values, that is P1, P2, P3, P4, are actually lying outside the fitted line. This means that they are actually closer to the fitted line, but they are lying outside. So whenever we are working on this, we should reduce this distance from the fitted line, and thereby we should take care of the errors. So this error is basically the difference between the actual value and the fitted line that we are observing. So this is absolutely very important in this case. How can we take care of this error? And to take care of this error, we apply the method of the least square regression procedure. So in this particular way, we move on to this particular slide where we see how the distances are being measured. So here also we refer to all the 4 points, and accordingly we find out the fitted line and we find out the E1. This E1 is basically the error which needs to be minimized. So what is E1? E1 is basically the distance between the P1 and the R1, and that needs to be reduced as per the regression procedure is concerned. Because R1 is on the line or the fitted line where it is showing the actual or the predicted value, and P1 is exactly the observed value. So if the difference between the P1 and R1 is on the rise, then the extent of the error is rising, and this needs to be minimized. So in this way, the minimization problem will come up, and since this difference can be either positive or negative, we actually sum up the errors, and thereby we go for the estimation procedure. So in this particular procedure, we start with the derivation in this manner. That is, let us represent the 2-variable regression model as yi, which is the dependent variable for the ith observation, I is running from 1 to n, is equal to beta 1. This beta 1 is the intercept term. This beta 1 is the constant parameter. After that, we have beta 2, which is considered to be the slope coefficient related with the exponential variable xi. What does it mean? If xi rises by 1 unit, what is the change in the yi? So that will be captured by beta 2. And uy is basically the error term. So that is making an econometric model apart from an economic model. So for an economic model, it ends up here only, but this is an addition to an econometric model where there is a relevance of this error term. Now we are going to estimate this error. This error is based on the population data, but population data is unobserved, so we take it from the sample observations and we estimate it. So the sampling data from where we get the estimated value of the residuals, which we pronounce at uy hat, which is equal to yi, which is the actual value, minus yi hat, which is the predicted value. That means this yi hat was on the fitted line, and this yi is the actual or the observed value that we are getting. Now in the next step, as we come on, yi minus beta 1 hat minus beta 2 hat xi. So this beta 1 hat and beta 2 hat are substituted from the estimated values of these beta 1 and beta 2, which are put in place of beta 1 hat and beta 2 hat. These are the sample observed estimated values. Now our question is how to go for the minimization of this error. Since the difference can be either positive or negative, we need to sum up squares. So when we go for summation ui square, it is basically the sum up of the difference between the actual value and the predicted value. As we all know, actual value is basically taken up from the actual observations which are plotted in the quadrant, and the predicted value is the value which is on the fitted line. And as we have already substituted the beta 1 and the beta 2 in this case. So as we substitute, we get summation of yi is equal to beta 1 hat minus beta 2 hat xi whole square. So this is basically substituting from the earlier equation, and we get this sum of square of error. Now as we go for the differentiation of this term with respect to the unknown parameters beta 1 and beta 2, we get these normal equations. So the first equation, as we can see, is summation yi, which is taken up by taking the differentiation term, which is given by is equal to n beta 1 hat. N stands for the number of observations, and beta 1 hat is the estimated value of the intercept, plus beta 2 hat, which is also coming up as the estimated value of the slope coefficient, summation xi. So this summation xi is already derived from the last step. After that, what are we doing? We are basically taking up the second normal equation, which is multiplying yi on both the sides, and finally we are getting summation yi xi, beta 1 hat summation xi, which is related with the intercept term, and beta 2 hat summation xi squared, which is related with the slope term. So in this way, these two normal equations are being derived, and they are the respective equations of the differentiation of the sum of squares with respect to the first variable, that is intercept, and the second variable, which is the slope coefficient. Now we get on to the estimated values of the beta 2 hat and beta 1 hat, because they are the estimated values of the slope coefficient and the intercept term. So when we go for the beta 2 hat, if we look at the numerator, then we can see that n, which is the number of observations, multiplied by summation of xi yi minus summation xi yi taken separately. This is because we have a covariance term which shows the association among the variables, and also we have the separate term which takes care of the variance. So after that, if we take the deviation from the respective means, we get the next step, which is xi minus x bar into yi minus y bar, and in the denominator we have the usual expression of xi minus x bar whole square, which is the variance. Now we go for the final term, which is summation of small xi small yi by summation xi square. Now what is this small xi? This small xi is the deviation of the mean from the actual value of the xi. So basically capital Xi minus x bar is referred as small xi, and capital yi minus y bar is referred as small yi. And accordingly we have in the denominator summation of xi square, which is basically coming up as the expression of beta 2 hat. Similarly, we have the expression of beta 1 hat. So when we go for the beta 1 hat, we multiply xi squared in the numerator, and thereby in the denominator we also get the expression of the variance, and from there by dividing by n we get y bar, which is basically the dividing by the number of observations, and then we have beta 2 hat x bar. So this is the expression of the slope coefficient, that is beta 2 hat, and this is the expression of the intercept coefficient, which is beta 1 hat. So here we observe two different estimated coefficients coming up, which is beta 2 hat and beta 1 hat. So on the basis of this, we can get into the most important term in this slide, which is called RSS, residual sum of squares. So basically what are we doing? We are basically taking up the sum of squares of all the errors based on the observations. If we refer to that particular graph, we have seen there are 4 points. So 4 errors are coming, E1 square plus E2 square plus E3 square plus E4 square. From that, we have estimated the model with y hat, which comes up as B1 and B2. What is this B1, B2? B1 is the name for the intercept, which was actually beta 1, and B2 is the name for the slope coefficient, that is actually beta 1. So in this way, B1 and B2 comes in. And finally, we have the expression of RSS, which goes by the sum total of the errors, which is minimized. So this is the alternative method of getting the same result as we have derived in the last slide. So here what are we doing? We are again taking the actual value of yi, and we are taking the difference from the expected value and we are squaring it up. Then we are actually substituting the predicted value of yi hat. Here the predicted values are in terms of the small b's. So what we get? y1 minus b1 minus b2, which are the estimated values of the slope and the intercept, and we squared the entire expression. And this is being done to get rid of the negative terms. After that, we have this expression by breaking the brackets, and finally we end up with 2b1 b2 minus 2b2 x1 y1 minus 2b1 b2 x1. So this is how we get the expression of this. On the basis of this, we are basically taking the differentiation that is to be done with respect to the b2 and b1, and we set the first order derivatives to be equal to 0. Because that is what we do in our first order condition of a normal minimization or a maximization problem. So this is a minimization problem. So we set the derivatives equals to 0 to get the normal equations as it is written in this case. So after this, we get the normal equations by solving the 2n beta 1, which is minus 2 summation of yi plus 2 beta 2 summation of xi. From here we get the first normal equation, which is 2n b1 minus 2ny plus 2b2 nx bar equals to 0. So if we just rearrange b1, we get y bar minus b2 x bar. So the same result we are deriving, but in an alternative method by using the differentiation and other notations. In the same way, we can even derive the substituting for b1, and again noting that we also derive the same way for this particular result. So in this result, if we start, summation of xi is nx bar. So what are we doing actually? We are multiplying 2b2 on both the sides. So 2b2 of summation of xi square minus 2 summation of xi yi, which is coming up from the previous step, minus 2 y bar minus b2 x bar. This is by substituting the expression of the b1 hat that we have got, and as I said, nx bar is multiplied. So after this, we get the next step, which is 2b2 summation of xi squared in the bracket minus nx bar square. This is very important because here it will be reflected as the variance, which is equal to, by keeping the equation on that side, we get 2 summation of xi yi minus 2n x bar y bar. So finally, if we square it up and we divide by n the entire observations, then we move on to this kind of expression of beta 2, or we can say here b2, which is an estimated value of the beta 2, which is covariance by variance. So this covariance is the numerator, which comes up for 1 by n summation I1 to n xi minus x bar, which is actually represented by small xi as we have done earlier. Yi minus y bar actually represented by small yi, which is already derived earlier, by the variance. So this gives rise to covariance by variance for the beta 2, and similarly for beta 1 also the same thing is being done. So these are various alternative ways of showing the estimated value of the b1 and b2 respectively. So in this particular process, we can see that b1 and b2 are actually derived. Now we take up some of the specific examples in the context of bivariate regression model. These examples are basically the practical exposures to the real life data. Suppose the data is collected on infant mortality rate and its relationship with female literacy rate. This is basically coming up to be an econometric model where infant mortality rate, as mentioned by IMR, is a function of FLIT, which is the female literacy rate. So in this particular model, we are having the two important terms, which is alpha 0, which is basically the intercept term, and the beta 0, which is basically the slope term. And we have the error term epsilon 1. So when we refer to this alpha 0 and the beta 0, they are basically the slope and the intercept coefficients, and the error term is given by epsilon 1. So after the estimation of the model by using the ordinary least square, we get the predicted value of IMR, which is IMR hat, written by alpha 0 hat plus beta 0 hat FLIT. Now if we refer to the equation of this estimated equation, we find out that 117.6 is the estimated value of alpha 0 hat minus 1.07 is the estimated value of beta 0 hat. So in order to understand the estimation procedure of this model, we need to say that the slope term is given by minus 1.07, which means that if there is a rise in the level of the female literacy, then definitely the infant mortality rate will come down. So this coming down of infant mortality rate is very important in this particular finding. And accordingly, we have the standard error, which is given by 14.72 and 0.22 respectively. Now when we refer to the probability values, these are very important because they are actually referring to the test of significance. We see that the 117.6 appears to be statistically significant, which means that it is significantly affecting the IMR, as well as beta 0, which also happens to be the same. So in this particular model, the estimated results is acceptable. And the confirmation is done by this R square, which is given by 57.63. So when we go for 57.63, it means that 57.63% of the variation in the IMR can be explained by the female literacy rate, and the remaining percentage is unexplained. And this basically explains that the explained proportion is more than the unexplained proportion, and hence the model is highly acceptable. And moreover, the intercept and the slope coefficients are also significant. Now if we go to the next example, which is again on infant mortality rate but on the child immunization rates. This is also in case of the health sector, where the data is collected and the results are estimated. In this result also we find out that 56.4 is actually explained and the remaining part is unexplained. So this is also giving a very good goodness of fit for the model. At the same time, the coefficients happen to be statistically significant, and thereby the model is acceptable. Now when we go for the example 3, we find out that IMR is a function of per capita net state domestic product. This also goes back to the same kind of inference where alpha 2 and beta 2 are estimated. R square is 32%, but in this model 32% is too less. So unexplained proportion is more than the explained proportion, and hence there is no need of interpreting of these slope coefficients or intercept coefficients, because the model turns out to be unacceptable. So in the summing up, we can say that the regression analysis is very important to consider a kind of a relation between a dependent and independent, and in an econometric model there is a relevance of an error term. Whenever the error term is included, we have to be careful about the satisfaction of the OLS assumptions, otherwise we cannot carry forward. Thereby we go for the estimation. For the estimation, we follow the method of ordinary least squares, where we actually sum up the errors and we minimize it, and thereby using a particular derivation, we get the expressions of alpha hat and beta hat and the slope coefficients. And finally, we go back to the multiple regression model, which means that when we take up more than one independent variables. So this module actually discusses about the estimation procedure, about the relationship between independent and dependent, and finally we also discuss with some illustrative examples. Thank you.